All right, we've hit 11 o'clock. We'll go ahead and get started. Hello, everyone. Welcome to today's Open Teams community event. Really appreciate you coming. Open Teams is working to build a premier network of open source experts, our open source architects, as part of our overall goals focused on supporting and sustaining open source. I'm Brian Skin, the Open Source Architect Community Manager here at Open Teams, and I will be your host for today. Today's event is focused on the Python programming language and its distribution and packaging story. Anyone remotely familiar with Python is likely aware of the fraught reputation of this story and may be familiar with the long series of recurring discussions on the topic, going back well over a decade at this point, including a significant amount of discussion earlier this year on Python discourse and in a panel episode of the Talk Python to Me podcast. Those recent discussions have for the most part been focused on projects under the umbrella of the Python Packaging Authority, the PYPL. However, there are many projects involved in Python distribution and packaging that are outside of that umbrella. And at today's roundtable, we have 13 maintainers booked across 9 projects here to discuss the roles their projects play in this space. To note, we do recognize that there are many more projects out there that aren't represented here, as well as a significant amount of diversity that is not represented here in this first event. We are open to and planning on holding more events like this one if there's interest. And if you have projects to suggest or maintain a relevant project, would like to participate, please reach out to us at connect@openteams.com or on Twitter @OpenTeamsInc. In today's event, we'll start off hearing from Travis Oliphant, CEO and founder of Open Teams, to provide a bit of his perspective on the packaging and distribution topic and to frame Open Teams' posture with respect to the topic and with respect to this event. After that, we'll hear a brief intro of each of the projects represented, touching on things like their origins, their functionality and their purpose, and outstanding pain points that they have in what they're trying to do. After that, we'll take a brief break, and then we'll return with the roundtable portion of the event. And here, we're anticipating a focus heavily on the target audiences for the projects, use cases met, and those outstanding pain points. Given the size of today's event, we don't specifically plan on taking any audience questions, but please post any you might have into the Q&A, and we'll address them as we have opportunity. So with that, let's go ahead and get started. Thank you all for being here again. Travis, I'll pass the mic to you for your opening comments.
Thank you, Brian. I am so excited to see everybody here. I realize it's a small fraction of the folks that are actually caring about this topic, and there are many people here. Hopefully it just continues the discussion. I know the discussion has been happening both on discuss.python.org for the past, actually, I would say 28 years that we've been doing Python and technical programming. I have been involved for a long time, starting the SciPy project all the way back when I first distributed extension modules for Python. And Python became popular largely because it allowed a lot of people to connect to a language they understood and connect the libraries they relied on to that language they understood. And that intimately created a packaging problem from the very beginning. That packaging problem really amounts to, it's not just Python you're shipping. Right, you're shipping Python and you're shipping a lot of other things. So the fact that there isn't a C packaging story, there isn't a C++ packaging story, or has not been, really is part of the challenge we're facing. So that there's lots of different user stories around here, and I think part of it is the build, part of it is how who am I? What is my user story? What is my maintainer story? What is my perspective as a person wanting to get Python? I gave a talk at the Python Packaging Summit. The first time I'd participated for a long time, about 10 years previously, we had gone to the Python Packaging Summit and introduced Conda. It was the people who were there at the time, I think, were not really ready to have that conversation about what we were trying to accomplish with Conda, and so it didn't go very far. And then also kind of perhaps the bandwidth to engage. It does take time to engage in community conversations, and sometimes as a startup person, or you're going to have another job, like all of us have other jobs. That is a challenge. Like we talked about the diversity problem here. One of the challenges is just the fact that it's a volunteer community, and only the people that can show up and have the time to contribute are often the ones contributing, and people in their paid engagements don't get a chance to contribute. That's one of the things we're trying to do with the Open Teams events, is allow people to participate in the wider discussion and facilitate that wider discussion even as they're part of their job, help sponsor those conversations. So we've constructed this architect network or advocate network, or open source advocate, open source architect network, OSA, where we'll talk a lot about OSAs. They're just people like you who care about making better solutions with open source and having events that people can attend and share ideas. That's what that's why we're sponsoring this. That's why we want to do it. That's why we'll continue to do it. So really happy everybody's here. I've been a participant in this story, both as a maintainer of a library, trying to ship packages, trying to ship software, get in the hands of people. My first shipping of software was a tarball and a website. Pre anything else, it was really bad, really terrible user experience. But nonetheless, a few, really amazing people tried to download stuff and build it, install it, and then send messages on a mail and a patch file on the mail to try to say, hey, here's some things you could do. People have been doing that for at least 30 years, 40, 50 years, actually. But fortunately, we've got better tools now. Like the packaging story has gotten to where I saw it 30 years ago when all of a sudden a high school student packaged my software up for Windows, and I saw the use explode. I had something that was only a binary or a tarball source code only, and once it was packaged for users to install as an executable on Windows, massive numbers of people started to use it. So I've seen that for a long time, which is why a scientist like me ended up founding and being a part of a company that distributes Python, like Anaconda. So full disclosure, I'm not working currently on Anaconda. I do have a financial interest in Anaconda still. That said, I'm interested technically in just helping people get Python. My roots go back to just helping people get Python and get Python for use as a scientist and engineer. And I've seen ebbs and flows in that conversation. And I will report that the Python Packaging Summit was encouraging. I feel like the conversation we had was actually extremely productive while difficult. There are a lot of people in that conversation, and it's going to take, I think, multiple iterations to come to cooperative solutions. So I'm really thrilled to see everybody here, because I just see this as evidence that there's a lot of smart people who want to do something and want to communicate their use case. So thank you for attending. I'll sit back and listen and learn and see what I can do to help, and just see me as an ally and somebody who's interested in helping you serve your users. My main message to the PyPA was that Python serves a lot of users, and there's not one single way to get it to users that's going to rule them all. And that because of that, we need to recognize that the PyPA should be essentially serving people that serve users, rather than thinking of the PyPA as only serving end users. PyPA actually needs to be thinking about serving people that end up serving end users. So a little bit of a kind of maybe an update to that was my argument, that's the mission statement should be. And there was a lot of reception to that, good thoughts and good conversations that distilled from that. And then actually several other people said the same thing. So it turns out I was, kind of preaching to a choir, honestly. There are a lot of people really wanting the same thing. But with that, I'll turn it over back to the audience, and Brian, let's hear from all the wonderful people that are here. Thank you.
Fantastic. Yeah, thanks so much for that intro, Travis. So yeah, we have multiple projects here, but we also have individuals who are part of the PyPA and of the CPython reference of implementation of Python. So we're going to start with some perspectives from them. So Yannis Lydell, please step in and speak as someone who is part of PyPA.
Thank you. That's really appreciate it. Let me start sharing my screen. I hope you can see this and you can hear me well. So I appreciate Travis's words just now, because I still am kind of reeling from the packaging summit at PyCon. I got to be honest, and I've been there for a number of years, and I've also been at the event that Travis mentioned 10 years ago. So that's fascinating. I'm here with multiple hats on. I have this small hat collection I want to showcase here. First, I want to start with PyPA. Obviously, full disclosure, I'm just one of many people in the PyPA, so please forgive me if I'm missing out details, of course. Summarizing 10 years of organizational backlog is not trivial. So where does PyPA come from? Just wanted to clarify that I set the record straight. I also did that at a packaging summit. That it was started in 2011 as a volunteer group that coming out of a solo maintainer situation with pip and virtual env. Someone basically was looking for to maintain pip and virtual env going forward. And because at the time, I and a bunch of other people were using pip and virtual env for exactly what Travis mentioned, like shipping websites and services. we were thinking, hey, how about we just try to kind of organize this in a more kind of a healthy and like a sustainable way. Obviously, we were at the time like limited in our understanding and experience with that as well, and that's where also kind of this weird name came from, because we saw a lack of authority in the Python packaging space. This was basically post distutils time, when CPython had already kind of gone through a first iteration of packaging technology or packaging development. And essentially it started as a kind of a volunteer effort only, and trying to kind of make sure things kept being maintained. Fast forward over 10 years later, of course, we have a governance policy for the PyPA, which is now over 100 members large, and covers 50 different types of projects, from documentation to standards and tools, both for the building of packages as well as for distributing and installing them. Not to speak of PyPI, the Python Package Index, of course, which is also very closely related to the PyPA. Obviously, one of the questions that came up in the preparation of this roundtable was that, does the PyPA distribute Python itself? No. We are always trying to derive our focus from the standard process that the CPython team is conducting, and with all its upsides and downsides, frankly. As you can see, the PyPA maintains a number of key parts of the ecosystem. Some of them are even competing with each other in terms of scope and functionality. Here are some kind of broad strokes answers, and forgive me if I'm kind of put a ton of information here on. The main point that I wanted to get across is that PyPA is focusing on helping the individual projects as part of the PyPA to kind of continue to be based on standards and community interaction, in such a way that I think it's actually covering half of what Travis was alluding to earlier. The problem, though, is that, of course, it doesn't, I think, go far enough with this. Such as, for example, it is not distributing Python interpreter, meaning that there is always a kind of a disconnect happening between the packaging standards and what's going on in the CPython core team. And of course, generally speaking, the means to, or the ways how the PyPA does this is by continuously approaching the standards process through the regular Python enhancement proposals. I think nowadays it's dozens and dozens of PEPs that were written based on the work that PyPA did, and slowly but steadily and then implemented in the various tools. I think the gist is, of course, that the PyPA wants to foster a community of projects that follow the standards. And the key item here is standard, and not kind of trying to wing it as what pip and virtual and did at the start when all this kind of started. And again, like terms related to the what is the lack of strategy or coherent strategy is, obviously there's many words written around this already on the Python discourse and forums, but it's obvious that the sheer number of projects and the sheer number of tools is extremely difficult for end users to understand and make sense of. And I think that's where the PyPA kind of needs to kind of, as a group, kind of figure out a way forward. So yeah, that's about PyPA. This was a whirlwind kind of a summary of what PyPA tries to do. Obviously, there's many things that happen over 10 years. I don't know. I'm looking at the group here. If there's any like immediate questions you want to jump in, or anything of the topics that you see worth kind of exploring.
We should probably reserve those for the roundtable portion. So we'll keep that in mind. If anybody does have questions they want to ask off of this, we can, Giannis, you can bring your slides back up at that time.
That's good.
So thank you for that very much. Let's move on to you, Steve Dower, who is a member of the CPython core team. Take it away.
Sure, thank you. And thanks for having me here. It's kind of interesting to be representing the CPython core team here, in part because it's an incredibly diverse group with just a huge range of kind of different goals and intentions and reasons for participating in CPython development, and kind of the majority of people involved are not actually interested at all in packaging or distribution for that matter. So I don't have fancy slides. I don't want to spend a huge amount of time. I would expect that anyone interested enough in this session is aware of CPython, familiar with it. It's not the only distribution of Python, and arguably it's not even a distribution of Python, as was mentioned earlier. It's the reference interpreter. It's an implementation of Python that kind of the primary deliverable, the main thing that we ever release is a source tarball, much like what Travis mentioned earlier, where that's still our model of releasing Python. We also, as a convenience, have kind of 2 or 3 members of the group who contribute binaries for Windows and Mac OS. I'm one of them, Ned Daly, and to a lesser extent, Ronald Aronson do Mac. We largely see that as a convenience. We're not trying to be distributors of Python in the way that a Linux distribution would, or a company like Anaconda is trying to do. That's not our goal. That's not our intent. And it really is a convenience factor for users. That said, it's clearly grown into something that's far more heavily dependent upon the fact that we do have pre-built distributions. We regularly get requests for continuing to do builds, particularly into security fix lifetimes of older versions of Python, which we deliberately choose not to do because that's not our model, that's not our purpose for being, and it starts becoming quite a drain on volunteer time to do that. And it is also, particularly on Windows, the de facto build and the de facto set of dependencies that CPython is expected to have does come from our builds. That's not something that we intend or something that we necessarily even want. We're obviously quite happy for all the Linux distros to be shipping their builds of it. There's various other builds of Python available out there. And we very much don't get involved and don't want to get involved in package management beyond the CPython itself and even CPython itself for that matter. So I'm interested to see where the discussion goes. I'm one of the people who's interested in packaging and wants package management and environment management to be as easy and as satisfying as possible for our users. I do genuinely believe that you can't have a good Python experience without package management these days. And so I want that to be good. So I'm largely here to kind of, I hope, provide some of that baseline starting point, but I do want to be able to take things back to the core team and advocate for them with the wider group in case changes do need to be made in order to better support the needs of these projects or the desires, the goals of the projects that are trying to satisfy those needs.
Great. That's all you have to share, Steve?
Yeah.
Cool.
I'm
Awesome.
sure I'll chip in later on with more stuff, but I'll take the time
Great.
then, not now.
Excellent. Thank you so much. So now with those 2 perspectives set, we'll move on to introductions for the projects, the packaging and distribution projects that are represented here. I'm running them in a sequence that we agreed on beforehand. The first project to speak, to be represented, will be Nix, and Frederick Doman, which of you will be taking that?
I'll take it first.
Okay.
Hey everyone, it's really great to be here. And I used to do a lot of Python 10 years ago, and I got into packaging story into Nix because of Python and the state it was 10 years ago. And I'm really glad to see all this progress has been made since. Yeah, I also wear a couple of hats. I'm part of the NixOS Foundation board. I run a company that helps people with Nix and so on. But today I'm here represented just to help out. I'll present the more general view of Nix, and Frederick will take over the Python specific bits, as he's more active maintainer for the last couple of years. Let me try to share this screen if it works. Entire screen. All right. Let's see. Can you see my screen?
Yes, you're good.
All right, thank you. All right, just very briefly, because Nix is a huge ecosystem, it's good to touch base. So we have the package manager, which main focus is reproducible builds, but not as in terms of binary reproducibility, but in terms of like how do we go from all the inputs and metadata we have to build some software and then use that and really pin it down and then build each thing in a sandbox and make sure that this as itself is a reproducible process. Then the other part of Nix, which is often confusing, it's also a language in which we describe this, which we kind of describe how the different pieces are built. Then Nix packages is a kind of like a collection of packages that we ship. We have, well, depending on what statistics you take, the most packages out there from different Linux distributions. And there's also an operating system Linux distribution built on top of all this. So those are the different parts of Nix that you should keep in mind. It was written more than 20 years ago. I think we just celebrated in March 20 years since the PhD came out, written by Elko Dolstra, and Python has been obviously around almost since the very beginning. And why was Nix made? It was kind of like an experiment to say, okay, packaging is a stateful mess. How do we like apply functional programming ideas to that and remove a lot of the statefulness that is there and how to make the whole thing simpler by changing the design patterns. And by applying that, as I said before, we want to go from working source code from source code to working software as a repeatable process. And one of the unique properties of Nix is that it's a source-based distribution, but you kind of get a binary cache of all the packages that are built, and in theory and in practice as well, going from source to binary should be the same as either building the thing or just downloading the binary. That's kind of like the base for the non-Python specific stuff, and I'll hand it over to Frederick to talk about the Python packaging and how things are in Nix packages right now.
Yeah, so the Python packaging within Nix packages, it's a major part of Nix packages. I would say we have well over 5,000 Python packages per supported interpreter. We have the several CPython interpreters, 3 at the moment, if I'm correct, as well as PyPy interpreters. Aside from the Python packages set, which provides primarily libraries, there are also applications that you'd like to have, tools that are written in Python. And this is also actually, I think, the interesting part if you look at it in distributions. Python is used in so many different ways. You'd like to use it as a library to develop against, to write your application. There are different scripts. There are a whole bunch of different types of applications as well, all with their different requirements. And that makes it challenging as well. Now, in Nix packages, we provide then tools, functions, you could say, for building packages. But also for building environments. So whereas it's outside of Nix quite common that you'd use, say, a virtual env to install packages within an environment, our functions take a bit different role. We have packages all installed by themselves, and then we compose an environment out of those packages together. And that has some pros and cons, I would say. A con, for example, is that we can't work with cyclic dependencies. But at the same time, because we have all the packages on the different prefixes, it's interesting because you can do a lot of concurrent builds and concurrent installations. That's another topic actually with Nix. We don't really have the concept of installation. You can create environments on the fly if you'd like to, ephemeral environments with a tool called Nix Shell. Yeah, and aside from like functions for building packages by hand, for writing expressions by hand. There's also a tool, for example, to work with poetry. Poetry providing a log file, which we can use as an input. This tool, it's called Poetry to Nix. It basically allows you then to lock your full application, not just Python dependencies, but also your native dependencies. And
Excellent.
a big strength for Nix, dealing also with native dependencies.
Very good. Okay, great. Thank you for that introduction to Nix. Next up is Homebrew. Mishka, Rui, who of you would like to start off for Homebrew?
Yeah, I'll try to just share my screen. I have some slides. Just a second. Oops. Okay. Do you see the slides?
They are not showing, unfortunately.
It's not working. Okay. So yeah, it's not working. So I'll just do without the slides. Maybe I'll just then explain what we had on the slides. Homebrew is the missing package manager for macOS or Linux. So I mean, this sort of subtitle or second name we gave the package manager was true like maybe 10-20 years ago when on macOS you had MacPorts and Think, I think. There were not that many package managers on macOS, and the goal was to provide a different way to install packages, and especially because Apple was not shipping anything. So in 2009, Homebrew was created, and in 2019, so 10 years later, we added support for Linux. Actually, you can also use it on Windows with the Windows subsystem for Linux. We are shipping around 6,500 open source packages for macOS and Linux, and around 4,200 applications or apps on macOS, Firefox, Spotify, whatever you want. If you use Brewcask, you can install these packages. They are not open source, so we make a clear distinction between open source and non-open source packages. Of course, you can also host your own non-open source packages in sort of external package, sort of what you call tabs. So it's an external repository. So the key features we have in Homebrew is that we are trying to always ship the latest version of the package. This might explain why we have also less packages than some bigger distributions, because it takes a lot of energy to maintain all these packages. But you'll always, like 99% of the case, you'll get the latest version. You don't need sudo to install the package. So the idea is you have a second package manager on your computer or on your server. The sudo thing is important for people doing science stuff, which want to install their science tools on servers which don't have where they don't have sudo access. So that's why the Linux version mainly exists. What we don't like is patches, so we try to ship the software as close as upstream would do. Maybe Python is an exception because we have a lot of sort of workarounds to fit it into in the ecosystem, but for most of the packages we don't like patches. We ship precompiled binaries, so you can install from source with Homebrew, but that's sort of not the goal for the users. And anyone can modify a package. There is no owner. So if someone wants to update Python tomorrow, anyone can open a pull request. So we ship Python 3.7 to 3.11. As soon as the Python is end of life, we sort of put it in a deprecation phase and it gets removed quite quickly. Took some time with Python 2, but that's now done since a few years. We ship Python for the 3 latest macOS versions. So the same when Apple ships one version up, we sort of deprecate the -1 macOS version. And Linux, we ship precompiled binaries. I think for if you use, for example, Ubuntu 20, then you would be fine. If you use older versions, you will have to compile stuff from source. I mean, there are workarounds. It works. But there also we try to be on the latest versions nowadays. We have around 840 packages that depend on Python directly. And what is important to know is like we make also the distinction between what is sort of an application, a Python application. For example, Ansible would be an application, command line tools. But a library like NumPy, for example, that's a library. We ship it because it's needed by some applications. But there are some libraries where we say, oh, if you can install it by pip, just pip install it. You don't need Homebrew for that. So that's how we make the choice between what we ship and what we don't ship. The goal is to ship applications, command line tools, that kind of stuff. Use Python to build stuff, but not really to ship the whole Python ecosystem. Yeah, last maybe things. What we are trying to do is, of course, always keeping everything up to date, and it's pretty hard in the Python ecosystem. There are quite a lot of breaking changes, so it's hard for us to follow up. I mean, that's also one reason why we have a limited number of packages. And as we don't like patches, as I said, as soon as we need to fix something, we upstream the patch for the projects for different packages. I mean, it's more an issue with the different packages than the Python tools, what PyPy would provide, or Python itself. It's just like projects don't update as fast as we do. And last thing is that we are vendoring a lot of libraries. So when you need to build your application, and we would use then Poetry or pip or whatever to make the list of packages we need, and we will ship all these packages with our package. So we are also starting to keep these up to date, mainly the cryptographic libraries for security updates. So that's something a little bit new we are doing nowadays, because vendoring leaves a lot of stale packages around in the ecosystem.
Mm-hmm.
Yeah, so that's all my side. And yeah, Rui, if you have something more.
I think at this point, for time constraint purposes, we should probably move on. Yeah, so thank you very much, Mishka. Next on the list is Conan. Diego, that's yours. Please take it away. And I will say, if any of the other speakers have slides, feel free to share them with me just as a backstop in case there are similar difficulties sharing, email or direct share.
Hi, everyone. Do you see my screen?
Yes, it's coming through well. Thank you.
Okay, perfect. So yeah, I am Diego, and I am one of the co-founders of Conan. And what is Conan? Because it's something that's a bit different from other packages. We're actually a C++ package manager that is intended to work in all platforms and with all build systems. So it is decentralized. We also care a lot about the use case that the users will be storing their own packages in their own server. And we are fully written in Python. And we also, the recipes with the user experience, they write Python also to represent the C and C++ packages. We are probably in the Python ecosystem, is not very well known, but we are used by thousands of companies in production in the C++ ecosystem. And we have been backed by JFrog for 6 years already. So this is what Conan is focusing on. It's focusing on creating binaries from recipes. So the recipes are Python scripts that represents the stages, the steps that needs to be executed to build something from source. But our actual concern is binary compatibility. We want to work in Windows, Linux, Mac, and all of these cases. So we really need to take care of what comes into a binary. So if you change any of the architecture, options, configuration, compiler flags, or even if you change some of your dependencies, and this is one of the biggest challenges in C and C++ binary compatibility, is your own packages also change, and your binaries also change and need to be recompiled. This is quite complicated, and this is one of the major goals of Conan itself. So what is our relation with the Python packaging? It's actually a bit strange. For example, tons of people in the C and C++ ecosystem, they don't even want to install Python. And this is, of course, complicated because Conan is a Python application. So, for example, we have to deliver to them an application executable that is self-contained that we create with pinstaller. But this is also something that also conditions us and many of the other approaches because we don't have a full Python environment. So that means that when users realize that, okay, I want to share Python snippets and I want to use them in all my recipes, and then we have to implement like a Python package management inside Conan itself that allows you to reuse Python code in your own recipes and also allows like extended things like, hey, your Python requirements can actually affect also your C++ binaries. If you bump the version, you create a new Python requirement with a new version, that is going to change your binaries downstream that are using that. We also have other weird use cases. For example, a typical one would be users that are creating C++ applications, but they have also Python embedded in the C++ application. And in that case, for example, they put CPython and they create a Conan package that has CPython inside to be able to link and use it as a C++ library, which can be done. And one of the major pains at the moment is Conan users, they want to use other tools that are developed in Python. And as we don't count with the full interpreter, then it's challenging. And there is now some work in progress that will be creating one virtual environment on the fly, because that also implies that you have different packages in the dependency graph. They can depend on different versions of the same tool, and they cannot collide. So in the same build, you will be depending on, I don't know, Meson 160 and Meson 060 and Meson 1. And that should be possible. So for that, we kind of need to create virtual environments on the fly to isolate every dependency and avoid version conflicts. So this is more or less. And this is Conan.
Terrific. Thank you so much. Moving on from here, the next one on the list is SPAC. Todd, Adam, which of you is going to take the lead on that?
Okay, I got some slides I can share. Where do I do that?
It's the screen with the red slash through it underneath the gallery.
It's a weird icon. Okay.
It is.
Let me, share screen.
All right, slides. Well, yep, slides are there.
Okay, great. All right. So I'm just going to go through the summary. I mean, I have the same questions as everybody else. SPAC is the flexible source and binary package manager for HPC and scientific computing. It dates back to 2013, but really started taking off in 2015 when we got folks like Adam on the project. It was created, I mean, mainly out of anger at how hard it is to build things on HPC systems. I had a grad student who had 10 or 12 things that she had to build on a BlueGene L machine, and continuously building and deploying those in different ways got old after a while. So I started working on this. It fills a gap for multi-language deployment. It's a very general system, and a lot of the applications that you have to deploy on HPC systems are like that. And so SPAC is fundamentally, it's not a Python package manager. It's an anything package manager, but it is written in Python, and Python is, as others have said, a huge part of the ecosystem. I think we have like 2,200, 2,300 Python packages now. As far as it goes with Python packaging, we do build and distribute Python interpreters. Sometimes they're embedded inside of other codes. Sometimes they're just the Python deployment for an HPC facility for lots of different users, and sometimes they're just built in your home directory. We can create and distribute Python packages. We have our own sort of system for doing that. You have to make a SPAC package, just like the other systems like Nix. We don't really have a good way to interface with PyPI right now, which honestly is probably my biggest ask for the Python ecosystem. If we had to get some sort of support, is providing the metadata that we would need to integrate PyPI packages with SPAC. It would greatly simplify our maintainers' work. You can develop and install Python packages with it, though again, it's not really integrated with PyPI or the other sorts of workflows that folks are used to today. And you can manage native and system dependencies in the interactions of your software with those things. As far as what we're trying to excel at, I'd say the core of SPAC is really the flexible dependency model. There are a minority of dependencies in SPAC are unconditional. You can build something with or without different options. You can inject flags into builds. You can add patches and stuff. And in some ways, we're kind of the opposite of Homebrew. We support multiple versions and different ABIs and things like that. You can basically write a package that says, I depend on MPI, and swap in any MPI implementation into that package. So you want to use MVAPIT or OpenMPI or whatever, we'll build it with any of those. And compilers and toolchains are first-class citizens. So essentially, you can build the same package with NVHPC or the Cray compilers or the Intel compilers just as easily as you can with GCC. I guess modulo how hard it is to build with those compilers. We're serving the use cases that are needed for scientific computing. So reproducibility is a big deal. That's why we have multiple versions and multiple options. We have teams that really want to build specific configurations of things. We have an environment abstraction, which is sort of a cross between a manifest lock file model and a virtual end. And then we serve lots of different types of users across the HPC ecosystem. So users will use SPAC to deploy in their home directory. Developers will use it to develop packages or large codes. And then HPC facility staff will use it to sort of deploy a big set of things across the facility and generate environment modules and things like that. We have a lot of support for developer workflows, and one of the goals of the project is really to blend sources and binaries seamlessly. So, if you have something built and you want to develop a piece of it, you can check out that piece, make some tweaks to it, and then rebuild the whole thing with your changes. So we want, not just reproducible environments, but tweakable environments. And some people use it as a dev environment. And then I guess I'll turn it over to Adam for the second slide here. So I guess I'll keep sharing, and Adam can speak to this.
Yeah, so I'll quickly talk about how SPAC has pros and cons specifically for the Python ecosystem. So as Todd mentioned, all of SPAC is written in Python. It's pretty easy to contribute if you already know Python. You don't need to learn Ruby or Nix or any other languages. We have multi-language integrations. So if you have Python packages that have non-Python dependencies in C, C++, Fortran, Rust, Java, etc., we can build those. We can also build C or C++ libraries that depend on Python. You can install multiple versions simultaneously. So for example, if you want to build something like NumPy with 3 different compilers and 4 different BLAS/LPACK libraries and benchmark the performance between them, that's really easy to do in SPAC. Everything is customizable. So for example, in other package managers, you might have a separate package for PyTorch with CPU support or CUDA support or AMD support. In SPAC, we have one package for PyTorch, and you can add and remove variants to specify how you want to build. You can even say, this is the exact CUDA Arch or AMD target that I want to build for. You can integrate with system packages. So for example, on HPC systems, a lot of the time you have pre-built MPI libraries that you want to use directly. So you can use that instead of building MPI from source, or you can build it from source if you know what you're doing. SPAC has really good hardware support. So for example, in HPC, we deal with a lot of esoteric architectures. SPAC has had ARM and PowerPC support long before Apple Silicon was a thing. So when that came out, a lot of our packages already had patches for ARM. We have a lot of effort going into GPU builds for NVIDIA, AMD, Intel. A lot of the developers from those companies actually contribute to SPAC. And I think one of the main benefits of SPAC is in terms of speed. So SPAC can target specific microarchitectures like Sandy Bridge or Skylake and inject compiler flags to build optimal binaries for those systems. Because everything is built from source, we have ABI compatibility guaranteed. We don't have to worry about libc mismatches that you might run into when you mix different conda channels, for instance. Of course, a lot of these pros also come with cons. So the benefit of building from source, you might have more configurability, you might deal with less ABI issues. Of course, building from source is much more time consuming. We do have a binary cache that you can use that has some packages, but we're still working on scaling that up. Compared to pip, a couple things that SPAC doesn't support yet, we currently model all of our dependencies in a DAG, so we can't have circular dependencies. So for example, TensorFlow depends on Keras, Keras depends on TensorFlow. Pip doesn't have any problems with that as long as they're both installed in the end. It doesn't matter which order they're installed in, but SPAC currently can't support that. Another issue is we can only have one instance of a package in our dependency graph at a time. So for example, a lot of packages like NumPy and SciPy will pin to specific versions of setup tools. So if you have conflicting requirements on those, we can't currently support that, but we're currently working on that. I think we're pretty close to modeling that correctly. In terms of platform support, we started off with Linux and quickly added Mac OS. Much more recently, we added Windows support, so we're a little behind on that. We can build Python and most pure Python packages, but any dependencies that need to build, for example, with CMake or NMake, those might need to be tweaked to add those build systems in. And SPAC is centralized, so all of our recipes need to be manually updated, and they have to go through a review process with maintainers. It's not distributed like pip or conda forge are. So this is a con because someone, usually me, has to actually review each pull request, but it's also a pro because we have a single set of maintainers who know what they're doing and can vet these changes, and that's really important for a lot of our DOE stakeholders. So to kind of summarize, if you're a power user who really cares about speed or customizability, especially if you work on HPC, SPAC is definitely the right package manager for you. If you're the average user who just wants a certain set of packages in an environment and you occasionally want to update them, probably pip or conda are more likely simpler to use for those use cases.
Excellent. Thank you both for that intro to SPAC. Moving on, next we have Conda, and Giannis, that is yours. Back to you for a Conda intro.
Okay, just a second. Need to restart the presentation. All right.
Okay, slides are good.
So as I already alluded earlier, I'm here also as a Conda developer, and here's a weird thing: is that turns out many of these problems are very similar. And I just want to highlight is that in my current day job, I work on Conda at Anaconda, despite the fact that I used to or started off with PyPA. But that's probably in our small ecosystem not super surprising because many of these problems repeat themselves. Anyways, so this is Conda. Just wanted to kind of highlight that there are multiple ways to seeing it. Like originally, on a historic level, Conda was created at a time when the so-called Anaconda distribution, basically a specific binary distribution of Python and various other data science specific packages, was created as a kind of the command line interface so that users can install these packages and handle the day-to-day of package management. This was ironically around the same time as many of these projects, as we just saw, were created. The big difference to PyPA, and for example, at the same time, of course, as Travis already said at the beginning, it took non-Python dependencies into account as well. So it was kind of a stepped one layer up basically, and trying to kind of solve that as well. And nowadays, and kind of to again, like lots of things happened over the years. Nowadays, it's more of a community of projects, like around 150 or more or less. Some are governed by the Conda community. Some are maintained by Anaconda, the company, and the majority, though, and interestingly, and here's on the right-hand side, you see kind of like a snippet from that. Many of those are out there coming from third-party organizations, companies, or just regular practitioners that want to kind of build their own workflow on top of Conda. Long story short, the community covers kind of the language agnostic packaging system, basically. And when we talk about Conda, that kind of, we try to summarize this and try to encompass everything, but it's obviously not going to be any, it's not going to be really helpful to do that. As an example, one of the largest channels, which is another way of saying, and one of the largest repositories where packages are stored and maintained, is, besides the commercial one, Anaconda Distribution, is called Conda Forge. I think a number of people mentioned it before. It's basically the open source variant that was started off by a number of people. I think some are actually here in this roundtable session as well, years ago, to more or less democratize the maintenance of the recipes. Basically, trying to apply community standards to maintain the nitty-gritty details of how to build the packages. Quite fascinating to see coming from the PYPL, where this is mostly left to the maintainers, the package maintainers themselves, to worry about. But yeah, okay. So as I mentioned, main scope, building a multi-platform language agnostic package environment manager. So it's kind of very similar to pip and virtualenv, except that it actually does a lot more than just Python. Yes, it is capable to also package and distribute and install Python packages, but it's not limited to that. On the contrary, it's you're also, the Conda ecosystem also distributes Python interpreters, of course, through these different types of channels. Anaconda Distribution is the one that is commercially supported by the Anaconda company that I work for. But there's like many other ways of doing things, and including the hugely popular Conda Forge community. What else is there? Like, there's, of course, build tools in the ecosystem, such as Conda Build, but many others also that try to kind of help build Python packages themselves. They can be done through the Conda native format called Conda files, but also able to create real files directly that is supported by the PYPL, like following the standards as much as possible. And they can be shipped through the basically central storage, which is the anaconda.org platform, which is probably not really aptly named nowadays. And I guess on the right-hand side, I'm trying to kind of go through, okay, well, what is the, if we try to summarize what Conda does well, I guess what I've seen, when I came over from PYPL, I saw an intention to kind of try to follow standards as much as possible if they are applicable to the specific package, basically for the Python packages and the various other Python-related things. Of course, Conda is trying to follow the PEPs if it's possible. But I also noticed that there is plenty of opportunity to improve this. So I think that's kind of, also what drives my work today at the moment, is trying to build bridges again, trying to make sure that, while the Python packaging ecosystem is evolving over time, also Conda needs to kind of catch up and make sure that it kind of stays grounded in the actual real world uses of Python packaging and meets basically the end users where they are. I think one of the biggest uncertainties and maybe weak points in my experience was that there's a misconception sometimes, or even confusion between the users of Python packaging tools such as pip, how that relates to Conda, and that there's this kind of it's kind of sometimes seen as one kind of defeats the other, but in fact they actually work relatively well together. I think that's kind of my kind of endpoint where I was going to that at the end of the day, I think most of these tools try to solve specific use cases, and it behooves us to kind of find common ground to figure out a way forward so that we kind of not reinvent no pun intended, the wheel again and again. That's, I think, my hope, at least, with these different. And of course, finally, this is also something that I showed during the Python packaging summit at PyCon. I went through a bit of the history of Conda and PyPA, and of course here maybe something fascinating for you here coming from the various other projects. There's many overlapping developments happening where I think, especially regarding how the projects are evolving, how they're kind of then organized on the repository side. Like when, for example, PyPI hit certain limitations in the scalability, PyPI had to be redone. Or when, for example, the distributing binary packages on the various platforms kind of came up more and more due to the new uses. The Menu Linux effort in the PyPI side and the no-arc projects on the Conda side, they're really similar. And again, even on the governance side, I want to say that there's fascinatingly, like basically very, very close developments happening. And I want to say that, it's, I think, no coincidence that I think we kind of come here and try to kind of make sense of this. And I'm really hoping to see what the various other projects are kind of, maybe they see themselves here as well in this timeline. That's it.
Great. Thanks so much, Jonas. Moving forward, the next project in line is EasyBuild. Kenneth, take it away.
All right, set on the screen share. And this should be the one. Is that popping up?
Yep, looks good.
Yep. All right. So, well, a bit of context. We're playing in the same environment, let's say, as SPAC is. So high performance computing, supercomputers, scientific software, and lots of swearing when doing that. EasyBuild specifically is a tool for installing scientific software. We do that on HPC systems, so we care a lot about the performance, which sort of implies that we build from source whenever possible. So I'm deliberately not talking about EasyBuild as a package manager. It's a tool for installing software. We don't do binary packages, at least not currently. You don't need to be an admin to use it. All you need is write permissions to the location where the software will be installed. So we have lots of researchers also using it themselves in their account. Like SPAC, it builds for specific CPUs, again, for performance reasons. We heavily rely on environment modules, which is a way to give end users access to the software that we provide or we install through EasyBuild. It's itself implemented in Python. It still supports running on top of Python 2.7. And we support everything upwards from Python 3.5. And for the rest, this is mostly details. So also different compilers that we support, different types of CPUs, different types of GPUs. We have close to 3,000 different software packages that's without versions. And we're not counting extensions in those. And Python packages are often installed as extensions, so on top of something else. And it's open source since about a decade. This is what it looks like if you're installing TensorFlow from source. So we were very proud that once we got that to work, that you can install TensorFlow from source. That's the detail here with a single command. And that took a lot of effort. In the background, it's going through various steps when doing the installation. And the ones that you typically customize are the configure, build, install steps, where things need to get customized for the particular software you're installing. Then zooming in on the Python stuff, the challenges we see in the EasyBuild community with Python software, the first one is not going to be a surprise. The growth of different tools to install Python software with is a pain, and it's, at least to me, it's doing more harm than good. New things are popping up all the time. And it takes time for us to figure out how they work or how to tame them and how to make them do what we want them to do. If people want to get some see me venting that frustration, you should Google how to make package managers cry. That's a talk I gave a while ago. Like SPAC, again, we install Python itself as well from source. So to some extent, it's just another software package that researchers need. And we typically have a dozen or so different Python versions installed, and it still includes also Python 2.7 because some scientific software still requires it, whether you like it or not. If there are any pre-built binary wheels, they are typically useless to us because we really want to build from source and optimize for the hardware that the software will be run on. One other challenge we see, and this is relatively new, is that the software stack is getting deeper and deeper. So about 2 years ago, we were getting installation requests for PyTorch directly. Now we're getting requests for something that depends on something that depends on PyTorch. So we're already 2 levels deeper. Another thing is, and I'm sorry for the previous speaker, is we're not a big fan of Conda. So in general, it's a bad fit for supercomputers for a variety of reasons, which I can get into if you want us to. So we actually actively discourage people from using it on our systems. And another thing that we struggle with a lot, and that's a bit separate from Python packaging, is the breaking changes in Python releases that happen over and over. And a big one that we're currently trying to deal with is the fact that distutils is being dropped from the standard library. So that's a pain to deal with for EasyBuild itself, but also for the stuff that we will be installing, the Python software we will be installing with EasyBuild. And here's a slide with a bunch of links for people who are interested.
Great. Thank you very much, Kenneth. All right. Ralph, I believe you are next with Meson Python.
I think so too. That's Brian. And all right, so change the tack a bit from distro managers. We saw a lot of them, a lot of very cool ones. Users typically have to pick one of them. Meson Python is a build system. So
Ralph, if you have slides, they're not showing.
I was going to do the history first and then show a slide.
Gotcha. Okay,
because in the laptop, I'd like to not only see a blank screen with my own text. So I'm sorry, Kenneth. My tool is that I'm talking about here is one of those tools that is really new and that you're going to have to adapt to, unfortunately, as all of the package managers have to. So Meson itself is just over 10 years old, just had its 1.0 release. It's a general purpose build system. Meson Python is very new. It actually started only like 2.5 years ago, where Steve is here. I think it was Steve Spap that said distutils is going to disappear. So I was the maintainer of NumPy to distutils, which was very large and builds NumPy and SciPy and a bunch of other things. So my first plan was, well, wait a bit till setup tools adapt, and then we're going to upstream some things in setup tools, and we just carry on with the same stuff. And it turned out quickly that was like not going to happen. It was too complicated. So I decided to bite the bullet, and thanks to a lockdown, spend a ton of time on learning Meson and building SciPy with Meson. And I think if you can build SciPy, which has C, C++, Cython, Fortran, and a bunch more stuff, you can build pretty much anything. So that worked after like 6 months. And then 1.5 years ago, we decided that, well, now that works, we need a build backend. So because you need to be able to type pip install package name, and it needs to work. So for that, you need a build backend that is basically a thin layer between the build front end, so pip or PyPA build that the end user or the packager uses, and the actual build system that does all the really heavy lifting, like actually building extension modules, invoking compilers, those type of things. Let me share my screen. So this is my one slide on what Meson Python is. So its goal is to provide a best-in-class build system support for Python packages containing native code. There's tons of build backends. Most of them deal only with pure Python code. So Meson and Meson Python can deal with every language that's relevant, I would say. I haven't seen much actual work with Rust yet, but it should handle Rust just fine. Fortran, Cython, C, C++, so on should all work. And it's supposed to be a really thin layer, so it's supposed to just forward commands from that the user types, and might pass on build flags, compiler configuration, other options that are package specific. So Meson Python has an interface for that. Its main job is to pass them on to Meson, get the build done, and after that is done, kind of repackage it and then produce an sdist, a wheel, or an editable install. So those are basically the three outcomes that you get when you use it. And I think it's important to emphasize that a wheel here is mostly, it's either usable on the local system or it's an intermediate state. So if you're packaging for spec or for Nix or for whatever, you're still going to probably use either pip or build here, produce a wheel, then install that wheel, and then repackage it into the native format that you distribute to your end users. So that's what it is. I guess this is as good a time as to announce that it is ready for general use. I would say that is the first recent highlight. I'd say, for the last 8 months or so, I think a few projects have been doing releases with it. They went pretty smooth. Life is much better post distutils, so I encourage every package author to give it a try. Editable install support is the most recent major feature. A nice thing is that it also automatically rebuilds if you change a file in your C code on which your extension module depends. Like, it knows about that and it will automatically rebuild, so you don't have this weird split where pure Python edits do the right thing and everything else does not. There are also a bunch of spin-off benefits, because I think we were the first build backend to do really non-trivial things. I think Henry's talking after about scikit build core, which is maybe even a little newer, but does very similar things. We had to improve config setting support in pip because the interface in pip was pretty limited. We had to make some changes in Cython to do things like improve tab file support, and we had to change things in Meson itself, like adding support for Cython as a language. Got a lot of help from the Meson developers for that. Then the challenges that we faced, well, there's quite a lot. It was actually a lot harder to write a build backend than anticipated. The first, I think, biggest missing feature is still cross-compilation. It kind of works with cross-env, but not really. I think Meson has good cross-compilation support, but Python as an ecosystem, there's lots of work left to do, and we're actually invested in doing that. Dealing better with API and ABI constraints. So things like NumPy that have a C API, where you need to put more constraints on your wheel than you have on your sdist. There's still I'd say an active discussion on how best to do that. The biggest one in the context of package managers is discovering non-Python dependencies. And a big pain point we have there is that it's different in every distro. Say you need a Blast library, and you can do that through package config or through CMake or through config tool. You find a corner case in every distro, and since there are dozens of distros, including the Linux ones, everyone does something slightly different. So that might be my biggest ask for the distro folks here. Just don't do non-standard things. Ship package config files. Don't do things like build Open Blast without layback support. Yeah. And then Windows compilers, that's I don't know if it's Microsoft's fault or it's Fortran's fault, a bit of both. But Windows compilers are a massive headache in general, but especially when you have Fortran code as well. So that's our biggest challenge. I'll stop sharing. I made one ask from the distro folks. Let me also if I have one for Python packaging, community. I'd say the way front ends and build backends work is okay. What needs improvement is basically the metadata model. Also to address things like that Todd mentioned, there's just not enough metadata for it to work outside of the fairly limited PyPI ecosystem. And it needs external dependencies. It needs the difference between what's a a build dependency versus a host dependency when you're cross compiling and so on. And it needs a split in PyProject.toml because that's now really PyPI specific and not project specific. So you can't map what's in, things, dependencies are over constrained for PyPI, and the actual constraints are looser when you do it in Spec or Conda or something like that. So that kind of area needs work.
Your way.
Right, that's what I got. Thank you.
Thank you, Ralph. Really appreciate the overview and the thoughts on directions for standardization and improvement. As you mentioned, the last package that we have to introduce is scikit-build. Henry, that's yours. Go for it. Yep, slides are good.
Yep, just have to unmute. Okay. All right. So I'll just leave that on the side. Hopefully nobody minds. Yes, so I work in several different areas, though scikit-build is probably the main one for this. I'll mention a few others. So I'll start with a quick history of scikit-build. Scikit-build actually goes back to about 2014. And it was originally built on top of distutils and setup tools because that was it. That was the only way to build packages back then. And there have been a lot of developments since then that have been really helpful, especially for a backend like that wants to really wants to do the build itself and doesn't need help from distutils and setup tools. And there really are some great Python backends existing, but scikit-build was and compiled backends didn't really exist at this point. This is a little before Meson Python had started when the initial proposal started being written for this. And it actually ended up getting, one of the proposals ended up getting funded. So I'm on a 3-year NSF project to work on scikit-build and scikit-build core. And that started about half a year ago or so, and was going over the next, and goes over a total of 3 years, sort of to build this into a useful modern backend. So the original scikit-build is still being maintained, and we're planning a path forward for it, but it's built on the setup tools, distutils design. It's all built on top of a setup.py and has all sorts of issues with that. There are a few benefits, but setup tools really isn't a great thing to extend. There's just a lot of legacy code there. There's a lot of things that that setup tools is already extending that it's difficult to extend again. It's just a really difficult system to work with, and has lots of downsides, like just specifying that you want the CMake wheel, but only if the CMake is not already installed on your system. That sort of thing is difficult to do properly. And so scikit-build core is a new design designed around the modern PEP 621, for example, the PyProject.toml configuration, where you just configure your project. You have a series of optional configuration tools. There's no setup.py. It doesn't interact with setup tools, distutils, or wheel at all. And then you use your CMake lists. And this is really useful for projects that either have an existing CMake build system. So I'm working with quite a few of them, like PyTorch, that have these giant CMake build systems, and would really like to just provide this. As well as new projects. I think I really like CMake. I've written a book on CMake. I've been working on it for a while, and I think modern CMake is actually quite nice. There is a lot of legacy code, but that's true with anything. And CMake can be very good if you do it correctly. So some of the these got flipped. So some of the considerations that have come up when working on this, the get requires hook in PEP 517 is really critical. It's how we're able to decide that we need to download CMake, or if we can use the system CMake. So if you're on a system that you don't have binary wheels for, this allows you to support that system, because there's just now a prerequisite: please install CMake first. And so if you're on PyDite or Android or Clear Linux or all these different systems, those can now easily be supported, while still allowing a normal user, if they want to build, will go grab that'll still go grab CMake for them if they didn't install it. Same thing with Ninja. This was also added to Meson Python. I'm actually in the Meson Python project too. Binary build backends really overlap with pure Python backends, plus have to do more. So been looking into various ways to try to share that. I've been modeling Scikit Build Core on Hatchling, and I would really like to be able to provide some sort of plugin for certain types of builds. I think some projects will always have to have or will do best with a custom backend, but some projects might be able to use Hatchling and then build plugin, and that would be a model that I'm working on in the sort of long term. Some of the things that are really important for us, caching the build directory is something that's important, especially if you're doing editable installs. In fact, for editable installs, isolated builds really don't make much sense. You can't throw away the build environment and then try to rebuild, because you have to rebuild for an editable install if you want things to actually be editable. So this is true for Meson Python and Scikit Build Core. I'm doing some work on standardizing dynamic metadata plugins, so the different build backends don't also have to develop tools to get versions from Git and to put together READMEs and things like that. And cross-compiling is a bit challenging. Though I think CMake is in a really good position for that. We're able to actually support Pyodide, whereas I don't think Meson is able to yet. A few things like that. But it's hard for all of us. I also work in several different other areas. One of them that's very closely related is the Scikit developer pages. So a few years ago, I wrote these tools originally targeted sort of the high energy physics community that it came from, but these are general, and I think it's one of the best sort of places to go for both a detailed guide over a bunch of different topics like testing, static typing, styling, packaging, both for the modern systems as well as there's the old classic one that was for setup.py, because that's what existed back when I started this. You'd have actions, Knox coverage, etc. There's actually, it's now several different things that work together. There's a cookie cutter with 12 different backends, including Meson Python, Scikit Build Core, Motrin for Rust, pure Python ones like Hatchling for Core. So a total of 12, all the generations tested, and it sort of follows its own guidelines. And then lots of suggestions for checks and things. And most of the packages I work on follow this. And you can even check and see how close your package follows this using the WebAssembly powered repo review, which is both a page as well as a Python package there. And I've been keeping that up to date. It just got updated with trusted publisher deployment, which came out at PyCon. I think we updated with about a day later. Okay. And this is what it looks like. This is the WebAssembly tool where you can just type in your repository in GitHub, select your branch name, and then it'll go through and check and see which guidelines you're following. And I'm working on hopefully making that a bit more general, maybe finding a place that like scientificpython.org to avoid the HEP in the name. Okay. I also work on CI Build Wheel. This is the standard, this becomes sort of the standard tool for building wheels on many Linux, MUSE Linux, macOS, and Windows. Supports Python 3.6 and up. There's currently a pull request to add Pyodide WASM wheels as well as an experimental feature. It supports cross-compilation in some cases, except on Linux, and ARM, etc. And can be configured from pyproject.toml or from environment variables. We actually there are some projects that are using this to build their own distributions as well, but it's really intended to be used. In the PyPI-like model where a package author uses it. Sets up their wheel builds, but it's meant to be really easy to build. Okay. Anyway, this is the sort of the various different things I work on. So I'm part of the Meson Python project as well. I'm also a PyBind 11 core maintainer and doing a few other things. And I've done quite a bit of teaching and training sort of in this area as well as in packaging.
Indeed. Great. Thank you very much for the overview of Scikit Build. So we are done with the round of project intros. At this time, we'll take a 5-minute intermission. My clock says it's 19 after the hour, so we'll resume at 25 after the hour Eastern time with the general discussion roundtable. So we'll see you in a few minutes. As the panelists begin to return to their seats, I'll introduce the roundtable, though honestly there's relatively little to introduce because we intentionally set this up to be a fairly unstructured conversation. We want to obviously focus on packaging and distribution, and in particular, what are, we've learned a lot about the use cases that are met and pain points. We want to dig somewhat into how the projects interrelate or how their audiences and their use cases overlap or not. But broadly speaking, we just want to let these maintainers talk to one another and see what useful insights emerge from that conversation. So one place to start potentially, Giannis, you had some things on your slides, questions about PyPA and questions about Conda, as I recall. We could start there, but if anyone else has something specific that they'd like to launch into, by all means, go ahead.
Yeah, let me share my slides again so that we have kind of the overview. And obviously, as I mentioned earlier, PyPI is many things, and as you just saw by the slides of coming, there are just many different streams of work basically happening at the same time covered by PyPA. So I'm actually interested to hear what the other members of PyPA here have been thinking about this, how I presented it, and see whether there's like gaps in the understanding of what PyPA does. And if not, that's also okay. I mean,
we have had Paul Moore in chat correcting. Very little, actually. So I'm sure he would have happily corrected more if he felt like he'd gone off track. But
it's great to hear. In case you don't know him, Paul Moore, he's one of the long-term maintainers in PyPA, and I think has been the PSF, sorry, not the PSF, the CPython core delegate for working on basically the collaboration between the PEP process and the PyPA, or one of them. I think the other one was Donald Stuffed, that I don't think is here. So I don't know.
Well, if I can throw out a topic then. I noticed a number of these projects are packaging CPython and distributing their own builds, and as such are unable to use wheels or binaries that are being published by the package developers. And I'm wondering what people think in terms of, is that a good place to be? Would we rather not have to do that? Or are we happier doing that? Or do we feel like we're being forced into it out of necessity? Where it's like, that's a solution we have. And it's the solution that virtually everyone who's made things work has gone with. But is it the one that we should have gone with? Or do we want to kind of get away from that somehow?
I guess I'm not sure why you say that means we can't use wheels, because we do both. Do you mean binary wheels?
Binary wheels, yeah.
Yeah. I mean, for us, we don't want to use the binary wheels because we're actually managing the native dependencies under them. And I mean, when we do use binary wheels, we run into bunches of incompatible dependencies. And so we mostly only use the pure Python wheels. So we really do want to control the build down to the native dependencies. So yeah, I think we want to distribute our own Python.
Depends a lot on the context as well.
Package maintainer hat on, like for NumPy and SciPy. Like building wheels on a variety of platforms is like a huge amount of effort. And we do it with extremely limited tools. Like, every package, has a DIY approach, right? While if you look at like, any of the distros like Nix, Spec, Conan, whatever, they have a nice build form. They have a uniform way of doing things. They have docs for it. So in hindsight, answering your question, like we need something for like, the developer, like I'm working on my package and I need a development version of something else, which is a wheel typically. But, I wish we didn't distribute wheels as complicated packages.
Yeah, and for us, I mean, we don't trust the binaries in the wheels. And so, a lot of the things that we put into building the SPAC build farm were about making sure that people can't slip malicious things into binaries in PR builds that then go on to get into, the public sign binaries. And so, we have a build farm that ensures those things already, and we kind of have to go through it. So, I think it's always puzzled me that PyPI doesn't have a build farm. I understand it's a volunteer effort and everything, and it's hard, but it does seem like something that would, improve the quality of like the wheels and enable you to do more consistent dependency management on the back end too. Instead of, like Rolf said, like I think looking at the building a wheel process is pretty daunting for most developers.
But as you point out, the complexities of having a wheel that has different dependencies from what's underlying it, and without having a distributor somewhere in that build farm to say here are the binaries for the runtime and the dependencies, then how do you have a build farm on top of that? Like, you wouldn't be able to use wheels from a PyPI build farm any better because they're not going to be built on top of. But alternatively, if such a farm did exist, then it would have some kind of spec for what its underlying environment is. And so then if you made your environment match that, you could use those wheels. And is that a world we'd rather be in?
Yeah, I think so. Because I think you've got, so there's two things that a build farm does, right? One of them is it produces binaries. And I think that's really the end result. And, we had a build farm before we started publishing binaries, and it was to check that things actually built, right? And that things, worked when we built them from source. And so, like you say, I think it would, you would have a more documented set of conventions, and you would enforce at least some consistency and a guarantee that a package builds at least a certain way with the build farm. And I guess, if you look at the SPAC build farm to some extent, like every package in SPAC is parameterized, right? Like you can build it 100, 1,000 different ways. What we're relying on essentially with the build farm and the choices that we make about sort of what slices of the combinatorial space to build is that, when somebody tries a completely different build locally, or, a slightly tweaked build locally, that it's likely to work, right? I don't think we're anywhere near 100%. But, I think a lot of users find that they try a build that nobody's done before and it does work, because and that's one of the goals of SPAC, is to enable sort of integration into new use cases.
I think another issue that you get when you push wheel building onto the developers is that you're really limited by how much compute resources you have. So if you only own a Linux computer or a Mac computer, you can't necessarily build wheels for Windows. Obviously, CI build wheel helps immensely with that. But having a dedicated build farm that both produces wheels for every system and ensures that things build correctly is super useful. I think it's useful to compare to other languages. So for example, for R with CRAN, or for Perl for CPAN, both of those have dedicated build farms for all packages that ensure that in an isolated environment, that package builds with only the dependencies specified. And they also have ways of describing and listing external dependencies as well, which Python currently lacks.
To what extent is the growth of ARM and maybe other stuff coming, like RISC-V, going to make this more complex? It already has, I guess, for ARM, certainly. But...
I think it makes it harder, because right now, our build farm's in Amazon, right? Like, or at least half of it's in Amazon, half of it's at the University of Oregon on dedicated machines. And for ARM, like we run out of spot capacity sometimes, right? Whereas for the other platforms, we can mix and match instances and get the capacity we need. And so, any kind of new architecture like that is going to be hard. The one that's really hard is power, because you pretty much have to own your own power builders unless you want to pay for IBM Cloud, which is, I don't know exactly who does that. And the GPU builders, I guess one nice thing about the GPU ecosystem is that you don't have to build on a GPU system for a lot of the builds, right? So like a lot of native builds will require that you run configure on a system that actually supports running the tests that you make. Or you build cross-compilation support all through your toolchain, which can be very hard. With the GPUs, at least you can have a build farm, but testing is hard, right? Because if you actually want to run on the GPU, like for AMD GPUs, we don't have that many AMD GPU resources right now. We will soon, but like we don't right now.
Regarding ARM on the Homebrew side,
Power is a good example, though. Something that we try to provide wheels for, and then we build them on Travis CI, which is very flaky. But IBM paid Travis some money to kind of provide open source projects free hardware, and then they try to get projects to build wheels for it. So NumPy has a bunch of wheels up for PPC 64LE, right? And then when they break, you're kind of debugging on CI because no one has the hardware, and so it'd be much better off like leaving that to people with like serious needs and a build form.
Well, or we're getting resources donated, right? Like I think that if you and we can say different things about IBM's support for open source ecosystems, but I think it's at some point, if the vendor wants, the biggest open source ecosystem out there, or at least the open source ecosystem for the biggest language, they could donate to a PyPI build farm and provide some resources for this stuff.
So Mishka, you had something to say?
Yeah, regarding ARM and hardware, it's an interesting thing because on Homebrew, we were sort of forced into ARM with the Apple M1 and M2. That sort of migration went, it was hard on the beginning, but it went pretty smooth. I was thinking about providing binaries for ARM on Linux on Homebrew too. We are not yet there. I mean, it means setting up the new CI and getting the machines. And I think the strategy around hardware, either you get sponsoring for it, or from a big corporation, or the strategy we are sort of using at Homebrew right now is using stuff like GitHub sponsors. People just give money, and then from that point on, you can spend it on hardware if you need to. Like the one part of we have one Linux machine for the long builds, which we pay on a cloud provider like Google or Amazon, that you can just pick whatever you want. But yeah, and the macOS runners are sponsored by Orca, I think. But hardware is a big issue, and having sort of stuff which is already pre-compiled for the users is important, but already for us, it takes a lot of time and energy, I think, to all the package managers here to have all this CI running.
And going back to the point, one of the points I made in the slides, we're actually cutting corners as well, because we're talking x86 and ARM, and oh boy, we're in trouble. But we're building generic binaries that run everywhere, and that means you're losing performance.
Yeah, actually, for Homebrew,
depends, right?
For Homebrew, the focus is not that much on performance, and that's maybe the difference with the people on the HPC or scientific world. They really need that performance. On our side, we just ship software that works for most of the people, 99%. And if you are in that 1% of people which wants to get more performance, then you need to build from source or find another solution like Easy Build or Spec.
But to some extent for Homebrew, it would be easier because the number of platforms you have to build for is a lot smaller. Like we're talking M1, M2.
Yeah, of course. We are doing like the 3 macOS versions. And then the Intel Macs are going to be deprecated soon. So at the end, we will just do macOS ARM and then Linux x86, whatever. But yeah, maybe that there is an opportunity to do 1 or 2 more platforms in the future. But yeah, we need to have the bandwidth for it. That's the issue. So it's not an adventure we want to start with right now.
It's a shame that you have this very powerful M2 ARM CPUs and you're not using them to the full extent.
It's I mean, if you really want to use Homebrew and compile from source, you can do it. It's at your own risk, and some people doing science stuff are doing it. Some are modifying packages and have their own versions of packages if they want to use different Fortran libraries, underlying stuff, change the compiler. You can do it. It's not that hard. But if it's broken, if it doesn't compile, we will not help you. It's up to you to fix your stuff.
That's the wise move.
So one thing I'm noticing now that we've heard all the intros to the packages and the conversation here, that there's a heavy scientific Python representation in this group. And one thing that I realize I don't know, obviously scientific Python uses a lot of compiled extensions. Are there other sectors of Python application space that use compiled extensions heavily, or is it pretty much exclusive to scientific Python? Getting lots of no's, so clearly there are more.
It's starting to be used more. Looking at our discussion, for example, you have packages like cryptography, right? It's a core package. It's used throughout. It used to be implemented, I think, in C first, and then was rewritten in Rust a year or two ago. That caused quite some issues as well for distributors.
It was the first Rust, yes.
Yeah.
Like major package. Pydantic is moving over too. So Pydantic core is Rust.
It's moving to Rust? Oh, cool. Yeah. I mean, cool. It's going to be work to change it everywhere, but yeah.
I think the other example is GUI backends. So for example, matplotlib, you can use PyQt, etc., and those are extremely difficult to build from source.
Yeah, PyQt is a topic because, I mean, Qt is already complicated to build. And once you've done that, then you start, I mean, right now, for example, the Linux build on our CI for PyQt doesn't work anymore. We didn't have time to fix it, but that's happening like each 6 months, 1 year, that either Qt or PyQt takes ages to get updated.
If you guys think PyQt is difficult, don't look at scientific software.
Of course.
Yeah, I would say one of the major differences between scientific software and other common Python kind of areas that do use native extension modules is those extension modules tend to be linking to the operating system more, and so they have a much tighter dependency on what's already installed on the system or what's going to be installed on the system. Database drivers are a big one where that's quite often an OS component, and the extension module is just going to be linking to it. So it gets really hard to build and distribute something that is going to respect whatever your operating system has. Cryptography comes up as well. Most everyone has cryptographic APIs as part of their operating system. Most of those cryptography packages include a full copy of OpenSSL because you can't distribute binaries that link to whatever libraries you may have on your system. And so you end up in easier to compile, but harder to know exactly what you're going to be linking against, I think, than a lot of the scientific software where you are more likely to know the entire stack, and it's a really complicated stack, but you mostly know about it when you're compiling.
So is that something that's, so again, the package managers that being represented, how solved a problem is that, or is that still something that's open?
How solved is ABI compatibility? It's not solved at all. It's a huge problem, and I mean, there's not even good tooling for it. Like, I mean, so yeah, that's, there's libraries like Abigail where you can do ABI diff and test, whether something's compatible. Red Hat uses that for integration. We've thought about, taking the symbols from Abigail and integrating them into like our solver, or checking for compatibility beforehand to solve directly for package compatibility, which I think is something that Wolf also was talking about on the prefix.dev blog. But we haven't done it yet. And I mean, I think a lot of the relationships between packages at that level require more sophisticated solvers than what we have right now, which is something that we've been working on in SPAC, is modeling, different aspects of ABI compatibility, or even, like with the GPUs coming into the ecosystem, right? If you want to do if you want to link software where certain modules have been built with like the GPU compilers, you need a certain linker for that because the regular ones don't understand the GPU sections. And so there are constraints that actually span like the whole DAG, where you have to know to use a certain linker in the toolchain. And if you want to tweak the package, then you have to know what to change across the whole graph. I think more work in the modeling space is kind of what we're focusing on would help that. I don't know what other approaches folks have had. I mean, I know Conda uses a bunch of ABI tags and things like that. And I think other ecosystems are similar. But yeah, just versioning software is really complicated, right? Like, I mean, you can get ABI breaks from version to version, and understanding that is not straightforward. And often the developers don't even understand that when they release a new package. I think the other thing that comes up in the HPC ecosystem along those lines is there are certain interfaces and things that are really only supported by compilers. So you may have a dependency on things like a language level. So you may need C++17 in one of your dependencies, right? And there is no C++17 package. There are only compilers that support C++17 and runtime libraries that support C++17. Same for OpenMP. If you need OpenMP 4.5 in your code, that's a compiler dependency. And so modeling that stuff is one of the things that we're working hardest on right now, because it's those are actual requirements people have that can't be expressed cleanly in any dependency model I know of at the moment. And I think this stuff flows into Python because it has such a scientific emphasis, right? Like with AI becoming huge right now, and then AI making other people realize that they can use those flops for more than just AI. You have a lot of people who are starting to care about performance and demanding this GPU units. So it's getting tougher, and I think it's going to creep into Python more.
Yeah, Prajun makes a good point in the comments in chat. I guess the two approaches really are restricting yourself to a known set of ABIs, which in large part is you build your own DAG, you build your own dependency set, and then we'll only provide the binaries that work together. Or a modeling approach like what SPAC takes. And that sounds intriguing to me, and I would love to hear how it goes. And I'd be slightly terrified that it's just going to explode into like a million possibilities for every single package.
It already does that. Don't worry. We've got that under control.
A billion, then. We'll add some orders of magnitude.
Even more. I mean, it's totally combinatorial, right? Like understanding the whole package solving problem is combinatorial. So I mean, we switched from sort of an ad hoc Python solver to one that's written in answer set programming. So it's Klingo, and that's enabled us to model a lot of this stuff, perhaps more cleanly than like the stat solver that Conda is using, things like that. But it's still like you run into this combinatorial wall for certain features. And so like some of the things that Adam was talking about, properly modeling them in the solver, you get exponential grounding in your logic problem, and it's nasty. So yeah, like ways to solve that would be welcome. But yeah, the ABI problem, the compatibility problem in general is I wouldn't consider it solved. If you mention this in the wrong, or go ahead, sorry.
So yeah, in Nix we do the same. We just have the whole DAG down to glibc, and even different glibcs don't work against each other well. Right. So even if it's bad, you get into problems. So the only way to really make this reliable, I think, is to go all the way down to system dependencies and run them separately. Anything else just will cause trouble sooner or later.
Yeah,
so in general, are people happy that distutils is being dropped from the standard library? Is that a good move?
We didn't care.
Because
we dropped one we tweaked one function and it's fine. You can still get that information elsewhere.
Yeah, but there's many Python software out there that assumes it's there because it's been there since, well, I know, a decade.
I mean, that's the nature of deprecations from the standard library. I'm quite happy that it's going. but I think I was the only person who ever updated it in the last 5 or 6 years.
Yeah.
Apart from updates that kind of spanned the entire standard library for various things. I'm happy with some of those responses, that it's been an easy transition, because that's kind of what I hoped. It was just never going to be up to date. And I mean, really good example is like the most popular version of Python we're seeing out there right now is 3.8, 3.9, depending on kind of what numbers you look at for what version of Python people are using. That copy of DistroTools would not have been touched since they were released. So it wouldn't know about newer versions of compilers, newer types of compilers, just wouldn't have access to them. And anyone using it wouldn't have access to them. And you start getting failures because it can't find certain things. So we hope that by removing it and kind of, and obviously it pairs with the PEP 517 and the build system specification pyproject.toml. So there's ways to get another package in there. And if it led directly to, scikit build and Mason development, great.
I think the easy build guys had more trouble with this because you guys are actually relying on loose version, right? For
yeah, but that part is that part is solved.
So,
we got rid of that, but that was a tiny thing. We could have avoided that, but we didn't. So that was a bit of a pain, and we're not fully out of the pain yet. We're relying on DistroTools for other stuff as well. But I'm wondering, do you think that's not going to cause, let's say, more chaos in the package management ecosystem in Python? I mean, I'm not trying to make you reconsider. I think that ship has sailed. It's clear you have your good reasons. I'm not doubting. No, I'm not doubting the decision at all. I'm just wondering if this is going to have a negative effect on making the chaos bigger.
Depends on your definition of chaos. In some senses, yeah, because 10 years ago, DistroTools was the choice, so there was less chaos by definition, and it didn't always work, and so you hacked around it, and you found ways to make your package work despite it, but you didn't have the chaos of which of 12 backends do I choose. So from that point of view, yeah, there's absolutely more chaos now, but arguably more choice is less chaos because you can choose the one that works best for you and update it more frequently, tweak it more sustainably, and still get your package to a suitable place without having to create, let's say, numpy.distrotools.
So there's no chance that there will be, let's say, a replacement for DistroTools in the standard library, like one tool that's highly recommended.
Not expecting it in the standard library.
Yep.
But pip will be there, and if you pip install something that depends on setup tools, it will bring DistroTools back. And if you pip install something that depends on a different build backend, then you never get DistroTools at all, but you get a working build backend for that package. So pip will remain there, and that has the ability to get the build tools that you need. Sorry, I cut someone off.
For us, the transition, I'd say the transition to using whatever the PEP compliant build tools was the hardest thing. I mean, Adam recently did that in the Python package and stack, and I think we would really like to use the lighter weight tools and not rely on pip, but that's proved hard for a number of reasons. One of them is that just the number of things in the Python ecosystem that assume bootstrapping from wheels doesn't work well in the from source package manager, and so the number of things we would have to vendor to rely on Hatch or whatever is, or I don't know, what's the one that you want to use, Adam?
I wanted to use build and installer to replace pip, and build had over a dozen dependencies that either already need to be installed from wheels before you can actually build any of them. So that was the issue we had with bootstrapping there.
I think a lot of those have been improved. I'm in the build team too. And I think quite a few of those have been improved. We now use Flit core.
Yeah.
So
I think the issue I had when I talked to the build folks is they were there's no dependencies for Python 3.12 and newer, and it's what about people who still support Python 2 or Python 3.5 or whatever? I think there's still a lot of dependencies for those. In SPAC, I really had to push hard to get us to drop Python 2 support, because there is a lot of legacy scientific software that still only supports Python 2. And there's no funding to transition that to Python 3. We ended up dropping those, and if people want to install them, they can use an ancient version of SPAC. But Yeah, we didn't have too much trouble with the transition away from distutils. I think pip automatically replaces imports of distutils with setup tools. So that wasn't really an issue for us, and we didn't really use it internally at all.
Yeah, well, whenever you have setup tools, that injects distutils, and pip sort of ensures that. Unfortunately, that stuff is also going away too. So I think dropping distutils wasn't the big thing. I think the big thing is dropping setup tools from the default environments, and that's happening. It's in the next. It'll be coming out in the next beta, I think, or whatever the next release is of Python. But I don't think we've seen that one yet.
But setup tools is not a part of the standard library, is it?
No.
No, but it was available
by default in virtual environments, and ensure pip injected it, and those things.
So the
it's really hard
injection
to get one
stuff
without it.
the injection stuff can be a problem too. Like so I mean, essentially with ensure pip, Adam originally committed ensure pip to our Python package, and then we realized that was non-deterministic. So it kills reproducibility because you're injecting essentially an arbitrary version of pip. So we ripped that out and started supporting pip ourselves so that we would actually get a known version and the provenance would be correct. Because if you just enable ensure pip, you'll get whatever latest is, as opposed to what the manifest asks for. And we have to watch out for stuff like that in builds frequently, because we do not want things fetching random stuff from the internet in the builds. I think locking that down is a really, really hard part of building a separate package manager ecosystem, because so much stuff assumes that it can download things. So we spend a lot of time on that.
Frederick, go ahead and say what you had to say, and then we'll have to wrap. We're running almost up on time.
Yeah, so in next packages, when we changed to, when we added PEP 5.17, 5.18 support, we also started to remove setup tools as a default package during the builds. So you had to explicitly add setup tools when there was a build dependency. Initially, these things were a lot of work because there were so many packages that still somehow depended on setup tools, primarily package resources during runtime. But nowadays it's not so much anymore. I think a lot of them have been fixed. So that's a good part. One other thing now, Todd, that you just mentioned, packages that try to download things during build time. Yeah, that's a big problem still. All the kind of things that can happen during the build, downloading, but also actually invoking other build systems. That gets increasingly common. So, for example, packages that depend on Rust that want to build through cargo, packages that want to invoke npm and download things. I think there's even a build backend nowadays that, if I'm correct, is being used by Jupyter that does that as part of the build system, and that's really problematic as well to package as a distributor. And this is getting more common.
Well, we could likely have continued conversing for several hours more, but unfortunately we are coming up on time for the event, and we'll have to wrap it there. Based upon discussions before and during the event, it seems like there's interest in more events like these, and Open Teams will be happy to facilitate those as people are interested. Please reach out to us. Again, connect@openteams.com, or me personally, if you wish, bskin, BSKINN @openteams.com. Thank you to all of our panelists. Thank you very much for your time, and to everyone in the audience for attending. I've been packaging my own Python for several years now, so I've been very interested to hear this conversation. We have recorded the event. We will be processing that and posting it on the Open Teams YouTube. Once that is up, I will send out a message to all the attendees, all the registrants, with the link to that. And there will be other artifacts coming out of this. We have to take stock of what we have and figure out how to publish everything and continue discussions going forward. So again, thank you so much, panelists, attendees, all. Really appreciate all the information shared and thoughts shared, and to be continued, I think. So thank you.